The flight to Mars will be a long one, too long for a crew to sit in a capsule. Habitat and supplies will also be lifted to orbit and assembled. Several companies have been selected by NASA to carry out studies for a suitable system to do the job. A bit of competition is always good for invention. Bigelow Aerospace, with its Expandable Activity Module, or BEAM, currently being tested on the ISS, will develop and test a prototype of X-Base, a 330 cubic meter expandable habitat. Boeing of Houston is developing a modular habitat system that leverages more than 15 years' experience in designing, developing, assembling on orbit, and safely operating the International Space Station. Lockheed Martin will refurbish a multi-purpose logistics module into a full-scale habitat prototype that will include integrated avionics and ECLSS. Orbital ATK will mature the mission architecture and design of their initial cislunar habitat concept based on the Cygnus spacecraft that now supplies the ISS. Sierra Nevada Corporation's space systems will study and refine a flexible architecture and concept of operations for a deep space habitat that draws on the lessons of 3 to 4 commercial launches to construct a modular, long-duration habitat. NanoRacks, in conjunction with its partners, Space Systems Laurel and the United Launch Alliance, referred to collectively as the Ixion team, will conduct a comprehensive feasibility study regarding the conversion of an existing launch vehicle's upper stage, or propellant segment, into a pressurized habitable volume in space.
So if you're designing spacecraft to be in the Mars orbit, then the studies we're doing on space station can be applied and help us design more durable spacecraft for that Martian atmosphere. MISSE stands for the Materials International Space Station Experiment. We do study the durability of polymers in terms of their mechanical properties with radiation exposure. And we hear a lot about the radiation exposure impact on humans for flights to, say, Mars. But polymers and other materials that are used on spacecraft can also degrade from radiation, and that's one of the things I study. The MISSE 8 experiments do take a little bit of time because we do very careful dehydration measurements of the samples after they've been in space. What we found is that the Teflon erosion rate is highly dependent on the amount of sunlight and possibly the heating too. You need to know which of these environments it's going to be exposed to because it'll erode at a different rate depending on the environment.
Assembling spacecraft in orbit and fueling them for the long journey to Mars sounds simple enough. On-orbit refueling is anything but simple. NASA have been developing a system for unmanned refueling for quite some time and have a test article on board the ISS.
We can take a pick-and-place robot, put the tool wherever we need it to be, and all it needs to do is drive that tool because the smarts are in the tool. So that's what we learned from working on Hubble, is you put a smart tool with the astronauts and accomplish, both things. You've got smart tools and astronauts working together. Now we're putting smart tools with robots and trying to accomplish the same type of things we did on Hubble.
Aimed at developing capabilities for servicing, even refueling spacecraft on orbit, RRM is like doing precise surgery at a distance, doctor and patient separated by the void and vacuum of space. It's tough, but the payoff is huge.
Robotics can do things that humans can't do in terms of precision, in terms of control, holding a particular spot for 6 hours while engineers on the ground debate what to do. We can't ask a human to do that.
The robot is a very stiff, rigid interface. It's not forgiving like an astronaut's hand. So we have to take that into account. When you push on something really hard with the robot, you build up really large contact forces. When the astronaut pushes on something, his wrist might give. He's got his own internal sort of software compliance running. But in order to accommodate the robot so we don't break anything, we have to build features into the tool, features into the software. Just getting the robot to go where you want it to go, and, they don't position precisely. So you have to do things like build lead-in into the tool. An astronaut can probably just get it right on there because he's right there. So we do have to do things to make them, very specific to robotic operation.
That task successful? Next stop, Mars.